Okay, let's jump right into this explainer and look at exactly why the internet explosion pushed traditional relational databases way past their physical scaling limits. For nearly 4 decades, the relational database was just the undisputed default. Every single application started out the exact same way: a create table statement, a foreign key, and a join. And honestly, it worked beautifully, mainly because the world's data was small enough to fit neatly onto one machine. But then the internet completely exploded. Suddenly, a single tweet could fan out to 100 million followers, or one abandoned shopping cart could trigger 10 different downstream services. Vertical scaling simply hit a physical brick wall.
Here is what we're covering today. 1. The relational wall. 2. Laws of distributed physics. 3. Storage engines. 4. The NoSQL families. 5. Picking the right tool. And 6. Production realities.
Kicking things off with Section 1, the relational wall, and why SQL stopped scaling. So the crucial point we have to get straight right away is that NoSQL actually means not only SQL. The industry's response to that massive internet explosion we just talked about wasn't just to invent a single new database. Instead, it spawned an entire category of databases, and each one made a very deliberate, surgical sacrifice to win a specific superpower. It's really the realization that the relational model is just a tool, not a religion. Choosing a database today is all about picking the exact right architectural superpower over a flawed one-size-fits-all solution.
Moving to Section 2, the laws of distributed physics, specifically CAP and P-cell-C. The foundation of literally every distributed system relies on the CAP theorem. It states that you have to choose between consistency, where every read returns the absolute most recent write, and availability, where every request receives a non-error response. Now, here's the dirty little secret that gets missed in 90% of textbook explanations. Network partitions are not optional. Cables literally get cut. Switches die. Because these partitions are entirely unavoidable, you must declare your sacrifice between consistency and availability in advance. Pretending you can have all three is a rookie mistake you will definitely pay for in production. And it goes further. P-cell-C extends this idea by pointing out that even when your network is perfectly fine, you still have to make a hard choice between latency and consistency.
On to Section 3, storage engines, the underlying engine that decides everything.
Look, your underlying engine absolutely dictates your system's performance. The two major heavyweights here are B trees and LSM trees. B trees, which are used by traditional databases like Postgres, update your data in place. They are highly read optimized. On the flip side, we have LSM trees, or log-structured merge trees. These are heavily write-optimized. They buffer your writes into memory and then append them to immutable files on your disk. So the rule of thumb? Pick B trees for read-heavy workloads. But if you need extreme write throughput, LSM trees are absolutely your best friend.
All right, Section 4, the NoSQL families. Let's take a rapid-fire tour of the 5 major database types. First up, we have document databases like MongoDB and Elasticsearch. I want you to think of a document database as a giant filing cabinet where a single folder holds literally everything about an entity. In a traditional relational world, assembling a user profile might require joining 4 different tables. A document model just collapses all of that into one document, one read, and one network round trip. It is fantastic for flexible schemas, like when you need to quickly add a new feature flag without taking down your entire system. But here's where it breaks down. It completely fails at deep cross-document joins. If you suddenly need to calculate averages across every single folder in that massive cabinet, your system is going to crawl to a halt. Next, let's talk about key value stores like Redis and DynamoDB. A great way to think about this is a coat check at a restaurant. Key value stores give you your exact item instantly. You hand over the ticket, which is your key, and you immediately get back the coat, which is your value. Because they rely on simple order of one hash map lookups, they are hands down the absolute fastest database architecture. Redis can handle over 1 million operations per second on a single node. But the catch? They can't answer complex queries. If you ask that code check attendant, hey, which of these codes are wool? They have absolutely no idea. They only know tickets and codes. Then we've got column-oriented databases like Amazon Redshift and Google BigQuery. Imagine a warehouse full of school report cards. A traditional row store gives each student their own cabinet. But a column store, it puts all the math scores in one cabinet and all the science scores in another. The data is physically stored by column on the disk itself. This setup is a massive game changer because it enables extreme compression techniques like run-length encoding. By reading only the specific data you need and utilizing techniques like vectorized execution and late materialization,
Column-oriented databases absolutely crush traditional row stores when it comes to analytical OLAP workloads. Fourth on our list, wide column stores, like Cassandra. Now, don't confuse these with the column-oriented databases we just talked about. Cassandra acts more like a massive, sprawling city of identical warehouses where writes are blazing fast. It uses a masterless architecture to achieve linear horizontal scalability. And its ultimate superpower? Tunable consistency per query. You can actually dial up the consistency for one stripped query and then flip around and prioritize availability for the next. It's completely built for time series data and massive, continuous writes. However, asking a random ad hoc query requires an agonizing trip to every single warehouse in that city. In joins, yeah, it doesn't support them at all. But wait, how do we handle super interconnected problems? Things like social networks, recommendation engines, or fraud detection rings. What do you do when the relationships between the data are actually the most important part of your data? Well, that brings us to our fifth and final family, graph databases like Neo4j. Instead of doing incredibly expensive relational lookups, graph databases use a brilliant concept called index-free adjacency. Every single node stores direct memory pointers to its neighbors. Think of it like just pointing directly at a friend's cousin. Boom, one hop, done. In a traditional relational database, trying to find a friend of a friend of a friend requires agonizing index lookups that will degrade your performance exponentially. Graph databases, though, can traverse those massive multi-hop networks in milliseconds, making them the absolute ultimate tool for things like fraud detection and complex social graphs. Moving into Section 5, picking the right tool and the decision framework you need. Because let's be real, a modern architecture almost never relies on just one single solution. This is where polyglot persistence comes in. It's all about mapping your exact access patterns to the right NoSQL family. In the real world, you might use Postgres for your strict payments, Redis for a lightning-fast caching layer, MongoDB for a flexible product catalog, Redshift for your heavy analytics, and Neo4j to power your user recommendations. You combine these distinct stores to heavily leverage their individual strengths. So step by step, you can use this simple mental algorithm to make sure you never pick a database just based on the latest tech hype. First, strictly identify your core access pattern. Second, determine your actual strict consistency needs. Remember, CAP. Third, critically evaluate your write-to-read ratio so you pick the correct storage engine. Fourth, realistically measure your data volume. And finally, step 5, assess your team's actual operational maturity. Running something like Cassandra at scale is operationally very heavy. Always choose a system that your current team can actually manage and debug at 3 a.m. Which brings us nicely to Section 6, production realities, or the stuff textbooks usually skip over. Picture this. Your on-call engineer is staring at a flat-lined graph in the middle of the night. It's a nightmare, right? You absolutely must build observability for these exact errors from day one. You have to actively design against hot partitions, where a poorly chosen shard key concentrates all your traffic onto one single node until it literally burns out. You need to anticipate cascading failures during eventual consistency reconciliation. In wide column stores, you're going to face tombstone proliferation, where heavy deletes cause massive compaction storms that totally tank your read speeds. And please never forget to monitor your cross-region replication lag and your connection pool saturation. Remember, averages lie to you. You always need to be measuring your latency at the 99th percentile. So, are you ready to stop just memorizing database names and truly start engineering and designing scalable systems? It boils down to this. The relational database asks, what is universally true about my data? But the NoSQL family asks, how exactly will my data be accessed? Both of these are entirely valid questions, but the fatal mistake is using the wrong question for the wrong problem. Once you master the underlying physics of how your data is actively accessed, you unlock true, massive scalability. So I'll leave you with this. What specific access pattern is secretly bottlenecking your current project right now? Think about it, and I will catch you in the next explainer.